Hello, you guys. We are on 7.3.3 notes, so continuing with independent events and the multiplication rule. So the first thing that you see is the informal conditional probability that we're going to be talking about. So conditional probability, and we'll get to the definition of that down here. But informally, so suppose a jar contains 3 white, 2 blue, and 5 red marbles. If you draw marbles from the container without replacing them, okay, then probabilities change as more and more marbles are drawn from the container. So let A be the event of getting a red marble on the first draw. So looking at probability of A, okay, is saying on top, remember, is the number of red marbles that would give me this event happening. So there's 5 red marbles total. Out of, there are 3 plus 2 plus 5, 10 total. So the probability of A comes out to 1/2. Again, you have a choice to write it as a fraction, as a decimal, or as a percent. Okay. Let B be the event of getting a red marble on the second draw. Now, this is the interesting part. Okay. B is a red marble, but it's on the second draw, which the second draw you don't know until the first draw has happened. Okay. Find the probability that B occurs given that we know that A has occurred. So we know that A happened. And remember, A is that we got a red marble on the first draw. Okay, using probability notation, we can express this probability as the probability, this is read as the probability of B given A. Okay, it's just a line down the middle of them. Okay, so we're saying we know that we have all of these things up here. I'm going to change colors. Okay, we have all of these things up here, but A happened, which means we got a red marble in the first draw. So this has now been reduced to 4 marbles. Okay, and now we're trying to find the probability of B given that we know A happened. Okay, so how many of these are left? So B was talking about an event of getting a red marble. There are now 4 red marbles. Okay, out of how many total are there? 4 plus 2 plus 3 is 9. So we have a 4/9 shot for the probability of B given A. Okay, how does this come? Because there are 4 reds left and there were 9 marbles left. Okay, so that's where we got our numbers in this one for. Okay, so get it more complicated. Let C be the event of getting a white marble on the third draw. Okay, so the first and the second draw have already happened. We're talking about the third draw. We need to know what happened on the first and second draw. So we're going to find the probability that C occurs given that you know that event A and B occurred. So we got a red marble in the first draw and we got a red marble in the second draw, which means I already did A. So I can change this to B by saying, okay, now that's become 3. Okay, using probability notation, we can say this as the probability of C, of the event C, but we have to know, so given that A intersect B, that both of these happened. Okay, so both of those happening is leaving us with what's right here. Okay, now C is saying that we got a white marble, not a red marble. So there are 3 white marbles left out of 3 plus 2 plus 3 gives us 8 out of 8 marbles total. And so that's what we get in that case. Okay, so in question 1, in those 3 examples there, you calculated conditional probabilities. We did it informally because you didn't know what they were. Probabilities that one event will occur given that another event has already occurred. For the remainder of this activity, you're going to compare conditional and unconditional probabilities for everyday situations. Okay, so notation for conditional probability, here's your definition right here if you want to highlight, is P of B given A. Okay, and it's read as the probability of B given A. Those are kind of the important pieces there. Okay, so number 2, pause the video in just a second and solve these. Be sure to justify your answer considering there is not always a right or a wrong answer. Okay, it says consider the probability pairs below. For each pair, state whether you think the conditional probability is higher, lower, or the same as the unconditional probability. So remember here, this is an unconditional probability. This is a conditional probability. It has that little bar, it makes it conditional. Therefore, your justification is just as important as your answer. Okay, so pause the video and then come back to my answers that I'm going to go through right now. So for letter A, it kind of depends. So the probability that a person has blue eyes, probably the person has blue eyes, given that the person is a Red Sox baseball fan. You may think to yourself this has nothing to do with each other, but I've had lots of good answers over the years. Okay, a lot of people will say that these are the same, but like I said, it doesn't matter if some people may say it's higher or it's lower. Okay, but a lot of people say that these are the same because if we talk about the probability that a person has blue eyes, let's say that 30% of our population on the earth has blue eyes, okay, versus the probability the person has blue eyes given that they're Red Sox baseball fans. So if we're only looking at the Red Sox baseball fans, if we say that this has nothing to do with their eye color, then this should stay 30%. But I was given one explanation one time that some people said that people that are Red Sox baseball fans are less likely to be Asian, for instance, and that's going to make up more of a population of brown-eyed or other colored-eyed. And so therefore that might change this. Okay, there are reasons for the other, but same is a good reason. Again, give yourself your explanation, whatever it is. Okay, going on to the second one, the probability that a student watches Thursday night football, or the probability that a student watches Thursday night football given that the student is female. Now, I know that this is a bit sexist, but it does have a pretty high correlation. Okay, so we should essentially say that the conditional probability is lower, so it goes down from one to the other. The probability that somebody watches Thursday night football, okay, let's say that half the population watches it, versus if you know that they're female, that they watch Thursday night football. The question is, do we think that the same percent of females do this? And most people would say no, it's going to be a lot lower. And so whatever you think from that, but it's going to get lower. Okay. And again, however you want to explain that, but usually we're going to say lower in that case. Okay, letter C, the probability that a person drinks a cup of coffee most mornings versus the probability that the person drinks a cup of coffee most mornings, given that the person is under 12 years old. I think almost everybody will say that this one's going to go down, okay? Because if you look at only the population that's under 12 years old, very few of them are going to drink coffee. So maybe this is 10% of them, but this is looking at the whole population. And if we look at the whole population, a lot of adults drink coffee, and so that might go up. Again, some other people have different opinions there. Give your explanation. There's not a right or wrong, but you need to give an explanation that makes sense for your categorization here. Okay, letter D. So the probability that it is going to rain versus the probability that it's going to rain if the sky is cloudy. Okay, so usually we say that if the sky is cloudy, that it's going to rain. It's going to be higher chance that it's going to be this way, because if the sky is cloudy, then the chance of it raining is going to go up. Now, I've had some different arguments in this one, but essentially the idea here is that you need clouds in the sky for it to rain. Again, there's lots of different arguments with that, but that's probably the best one that I've heard. Letter E, the probability that you roll a die and get an even number versus the probability that you roll a die and get an even number given that you know you roll a number greater than 3. Okay, so this one actually has a correct answer. There's no iffiness in this, gray area in this. Okay, probability that you roll a die and get an even number is you have a 2, a 4, or a 6. So that's 3 out of 6 sides to the die, and so you have a 1/2 or 50% chance of doing that. Okay, probably that you roll a die given an even number, given that you roll a number greater than 3. So if I know I have greater than 3, then I have a 4, a 5, or a 6 on my die. Okay, so that means I have 3 out of 6 possible right now. But I'm saying that you roll a die and get an even number. So there are 2 of these that are even out of the 6 total, since it's no longer the large group. Okay, and that is 1/3. And so, or sorry, that is 2/3. Or sorry, 2 out of 3. Let's go back here. So this is a 2 out of 3 because now we've lowered the sample space to 3, and 2 of those are even out of 3 total. There we go. And so that's 2/3. And therefore, the probability of the conditional one is actually higher. Okay, so there is no gray area to that one. That one is an answer of higher. Your letter F here, probability you draw a card from a standard deck of cards and get a face card. Okay, so this one is there are 12 face cards out of 52 total, and that will reduce to 3 out of 13. Okay, and then the probability that you draw a card from a standard deck of cards and get a face card, given that the card is a heart. Okay, so the hearts are going to reduce the deck to only having 13 cards in the deck. And if you look at your hearts, there are going to be 3 face cards. And lo and behold, you get the same thing here. So these actually are going to come out to the same. Again, there is no gray area on that one. Okay. So then it essentially says, based on your answers, decide whether the 2 events involved in the conditional distributions are independent or dependent. You should have decided that your independent events were A and F. Okay, the ones that you said the same. If you decided any of these were the same, then that's fine. But those are independent of each other. And your dependent events then should be B, C, D, and E. Okay, any of them that you said lower or higher, because the probability changes, is going to be your dependent. So this is the lesson that's going to hopefully make your independent dependent make a little bit more sense later on. Okay, so I want you to go through and answer these questions. Go ahead and pause the video because as soon as I switch to the next page, you're going to see the answers to these. If you have any questions on these, please don't hesitate to ask me. But you've got a picture here you got to look through. Go ahead and solve through those. So pause the video now. Okay, here are the answers to that. So go ahead and pause the video and check your answers. And again, send me an email if you have any questions. And we're going to finish with this last question. So mutually exclusive events. Okay, another definition here, are defined as events that have no outcomes in common. Okay, they're also called disjoint events. So to really understand this, we ask a question. Can mutually exclusive events also be independent events? Okay, think. Most people will answer yes to this. And the real answer is no. Now, some of you are going to wonder why. So I'm actually going to say and explain the reason here. One of them, the easiest to think about is if I talk about dice, okay, and if I talk about even versus odd on dice, okay. So even and odd, no outcomes in common. Those have no outcomes in common. But the question is, are they independent events? And what we now know about independence is that if I say that the probability of, we'll say that's even given that it's odd, okay, and we would talk about the probability of it being even, if these come out to the same number, then they're going to be independent of each other. If they come out differently, then they're dependent. Okay, so if we know that the dice comes out odd, there's only 3 options left, a 1, a 3, and a 5. Okay, and how many of those are even are none. But if we just talk about the probability that it's even, we end up with 3 even numbers, 2, 4, and 6 out of 6 total, which is 1/2. So notice that those two things are not equal to each other, okay, which makes these two events dependent, okay, and mutually exclusive. Okay, now with that example down, again, coming back to this, can mutually exclusive events also be independent events? Will that ever come out? Okay, so the answer again is no. Okay, suppose A and B are mutually exclusive events and the probability of B is greater than 0. Then if you know that B has occurred, there is no way for A to occur. So what we're saying there is that if you know that your odd has occurred, it's always going to be a 0 on top here. So this probability, the conditional probability, will always be 0. Okay, and the likelihood of this one being 0 is not very good. Okay, which means that they have to be dependent on each other. Okay, I'm going to repeat that again. Suppose A and B are mutually exclusive events and the probability of B is greater than 0. Then if you know that B has occurred, A cannot occur because they have no common outcomes. So they must be dependent. Use this as an example here to get through it. Okay, so that's all I have for you guys today. Have a good rest of your day.